Above Earth, a small light moves across the night sky. If you know when to look, you can see it with your own eyes. No telescope, no screen, just a bright point crossing the sky in silence, faster than any aircraft. For more than 2 decades, people have lived inside this moving light. They have slept there, worked there, repaired machines, watched hurricanes turn below them, and sunrises arrive every 90 minutes. From the ground, the International Space Station feels like one of the few human things in space we now take for granted. And that is what makes it so easy to misunderstand. Because the station isn't resting above Earth. It isn't parked in some clean, empty layer where gravity has been switched off. It's moving fast enough to keep missing the ground, yet still close enough that Earth keeps pulling on it in ways we hardly ever think about. If the International Space Station is already in orbit, and people have kept it up there year after year, why does it now need rescuing from a fall? Tonight, we're going to unpack that question, not as a disaster story, and not as a simple matter of old hardware or shrinking budgets, but as a problem that sits at the center of what orbiting actually means. By the end of this video, you'll understand why the station's place above Earth needs to come to an end, why keeping it up there takes constant work, and why the final decision may be less about giving up on it and more about choosing what happens while we still have control. If you enjoy exploring questions like this with me, subscribing helps others find them too. Sharing the video helps even more. Let's begin. Picture the station from close enough that it stops being a point of light and becomes a place. The long truss runs through the middle like a beam stretched across open darkness. Solar arrays spread outward in broad copper-gold planes. The pressurized modules cluster around the center line, each one connected to the rest by ports, joints, cables, and the practical hardware of a machine that people actually live inside. Earth fills the lower half of the scene, black space fills the upper half. Between them sits a blue line so thin it can look decorative. That image invites the wrong instinct. The station seems balanced, it seems settled, it seems like a thing that already found its proper place and now simply remains there. The numbers from the European Space Agency make that first instinct harder to trust. The station flies at about 400 kilometers above Earth. It moves at about 28,800 kilometers per hour. One orbit takes about 92 minutes. A crew member living there can watch roughly 16 sunrises and sunsets in a single day. Those figures do not describe a parked object. They describe a machine moving fast enough to turn dawn and night into repeating events inside one work shift. Try to feel those numbers instead of filing them away as trivia. A coastline slips past the windows, darkness arrives quickly, and the horizon begins to glow again before the mind has finished adjusting. The station never gets an ordinary morning or an ordinary evening. It lives inside constant motion. That constant motion is part of why the environment still matters. A structure racing around Earth that quickly does not need much atmosphere before tiny losses begin to count. That pace also changes what height means. 400 kilometers sounds far when measured from the ground. In orbital life, it is the altitude of a place that keeps circling back over the same planet, never settling, never becoming detached from the world below. If you were standing by a window on the station, continents would not sit beneath you like a picture. They would keep sliding away. The address is high, but it is still an address written by motion. Most of us learned orbit as a clean drawing. Earth sits in the middle. A smooth line wraps around it. The object on that line stays there because the line itself looks finished. It is a useful first picture, but it smuggles in a bad assumption. It makes orbit look like a lane painted in permanent ink. The ISS deepens that assumption because it has lasted for so long. It appears in school books, tracking apps, documentaries, and night sky guides. There are people alive who have never known a world without the station crossing overhead. Familiar things start to feel natural. Natural things start to feel permanent. NASA's reference material cuts through that feeling with a stubborn fact. The station is the largest human-made object ever placed in orbit, with a mass of more than 400,000 kilograms, around 900,000 pounds. That number matters because it forces the image to sharpen. This is not a compact capsule. It is an assembled outpost with rooms, racks, radiators, tanks, computers, plumbing, docking hardware, life support systems, and all the awkward geometry that comes from building a place in orbit over many years. Once the station is seen that way, size stops being a bragging point and starts becoming a responsibility. A small object can slip out of the public imagination for a while. The ISS cannot. It is too large, too famous, and too tied to people on the ground for its future to count as a private matter. The emotional picture changes as well. The station still looks steady crossing above the atmosphere, but it no longer looks simple. It starts to resemble a working place with a moving address. Crews arrive and depart, cargo comes and goes, waste has to be managed, orientation has to be maintained, docking operations have to stay precise. Even before drag enters the story, the station already belongs to the category of things that survive by continual attention rather than by passive endurance. Public familiarity hides that labor almost too well. A person on the ground may see the station for a few quiet minutes and think of it as a fixed landmark. They do not see the planning behind that pass. Teams on Earth are tracking the orbit, coordinating traffic, watching systems, and keeping a complicated habitat inside safe margins. The streak of light overhead is the visible result of work that usually stays out of sight. From the ground, though, altitude still feels like an answer. 400 kilometers sounds far above weather, far above roads, far above ordinary resistance. It sounds like the kind of height where friction and decay should finally give up. That is why the blue line beneath the station matters so much. What looks from far away like a crisp border is not really a border at all. It is a thinning. It is the upper reach of an atmosphere that fades instead of ending. The station is high above most of that atmosphere, but not beyond all of it. That one correction changes the entire mental picture. The arrays are no longer ornaments on a monument. They are surfaces moving at extreme speed through a sparse environment. The truss is no longer a rigid beam resting in perfect emptiness. It is part of a machine passing again and again through a region where Earth still has a say. If you were looking out from the cupola, the view would probably feel both immense and strangely intimate. Earth is not gone, it fills the scene. The atmosphere is not gone either. It has been reduced to a shining line, yet that line is enough to decide the station's future one orbit at a time. That is why the station stops feeling dramatic once the atmosphere is understood. The station cannot stay in orbit forever, not because somebody forgot how gravity works, and not because the engineering was careless, but because the place it occupies has never been passive. The beautiful still picture was always missing the cost of staying there. That cost is easier to grasp once the station stops being a symbol and becomes a place with routine. People sleep there, they exercise there, experiments run there, hardware ages there. When an object supports that much ordinary life, the real miracle is no longer that it once reached orbit. The real miracle is that so many systems have kept cooperating in a place where nothing supports them for free. Another reason that opening image misleads us is that it hides the station's interior life. Inside those modules, nothing feels ornamental. Air has to circulate, water has to be managed, crews have to eat, exercise, and sleep on schedule, experiments have to be tended with patience. All of that depends on a structure that keeps moving around Earth, whether anyone is looking at it from the ground or not. Once that ordinary life enters the picture, the station stops feeling like a point of light with a romantic aura around it. It starts feeling like a neighborhood that has been carried into orbit and then held there by steady technical work. That is why the image matters so much. The more familiar it becomes, the easier it is to forget how much motion and maintenance are hiding inside it. Look again at the blue line under the station. From the ground, it is the sky. From orbit, it becomes a layer so thin it can seem almost ornamental. Both pictures are true. Both can mislead if held too simply. Most people imagine the atmosphere as something with a ceiling. Aircraft operate below it. Rockets punch through it. Space begins beyond it. The image is easy to carry because ordinary life rewards hard boundaries. Rooms have walls, oceans have shores, maps like clean edges. The real atmosphere fades instead of ending. Density falls with height. By the time you reach the orbit of the station, the remaining air is extraordinarily thin. No one outside would call it weather. Yet the station is not moving slowly through that region. It is moving at nearly 8 kilometers every second, and speed turns a sparse environment into an operational fact. That is why the word over time matters so much. One pass through this thin upper atmosphere would barely deserve mention. The ISS does not pass through once. It returns every 92 minutes. It does so through weekdays and weekends, through seasons, through years. Tiny encounters that mean nothing in isolation begin to matter when the clock is stretched across decades. Patient forces are often harder to respect than loud ones. Rust is patient. Fatigue is patient. A slow leak is patient. Upper atmosphere drag belongs to the same family. It does not frighten the crew on any given afternoon. It still shapes the long future of the station. NASA states the consequence very plainly. The ISS continually falls toward Earth because of atmospheric friction and needs periodic rocket firings to boost its orbit. Hidden inside that calm sentence is a complete correction to the way orbit is usually imagined. The station is not floating because gravity has somehow been left behind. It is falling around Earth. The sideways motion keeps missing the ground. Drag changes the terms of that fall by taking away a little orbital energy. The wrong image to avoid is a strong downward wind. That would make the problem feel more dramatic than it really is. The better picture is softer and more relentless. Rare particles strike the surfaces of a very fast-moving structure. The effect of each encounter is tiny. The effect of endless repetition is not. An earthbound comparison helps. Imagine a heavy train rolling well on level track. If friction quietly shaves away a little speed mile after mile, the train does not stop immediately. Yet nobody would claim the speed loss is imaginary. The engine must keep restoring what the system keeps taking away. The station lives inside that same logic, only written in orbital terms. This is why altitude alone can be such a bad guide to intuition. 400 kilometers sounds remote enough to be final. In reality, it is a compromise height. The station is high enough to operate in what we call space, and low enough that Earth still writes into the details. That is why the blue line in photographs matters more than it first appears. It is a hint that the station still lives on the edge of an environment, not outside all environments. There is no ordinary sensation on board that announces this drag. The crew does not feel a steady headwind. The clue shows up in tracking, planning, and operations. That hidden quality is part of what keeps the public picture so incomplete. If a force makes no noise, people are tempted to treat it as theoretical. Engineers do not have that luxury. A force that can change the orbit over time is a real part of the mission, whether or not anyone feels it directly. This gives the story a personal scale. If you were on the station, looking out at the thin blue atmosphere, you would be seeing more than scenery. You would be looking at the thing that keeps making the future expensive. The layer is beautiful, but it is also the reason orbit never becomes a solved problem. Another way to say this is that the station never finishes meeting the atmosphere. It meets it on routine days and on historic ones. It meets it during crew handovers and during quiet months. There is no moment when the orbit suddenly becomes a solved problem. The same thin layer keeps taking a little from the station every time the station returns to it. That helps answer a common instinct. People hear that the air up there is extremely sparse and assume the whole effect must be too small to matter. Sparse is not the same as irrelevant when speed and repetition stay so large. A faint rubbing can still reshape a long journey if it never stops. So yes, the orbit decays. That statement is true. It is also too short. The larger correction is that decay is not an occasional emergency interrupting stable life in space. It is part of the condition of being in low Earth orbit. The station stays overhead because that condition is measured, corrected and paid for again and again. Once that is clear, the blue line under the ISS stops looking like a decorative border between Earth and space. It becomes the visible signature of the force that keeps turning permanence into work. Seen from mission planning, that thin air becomes less like scenery and more like accounting. Nothing dramatic needs to happen on a given orbit for the problem to be real. Operators only need to know that the station keeps returning to the same physical bargain. It is moving fast enough for tiny losses to matter, and it is doing so often enough for those losses to accumulate. That is the kind of process human intuition often underrates. We are better at respecting the loud event than the quiet one. A hard impact commands attention. A small subtraction repeated thousands of times does not. Yet orbital decay belongs to the second category, and the station's long life only makes that category more important. The whole later story about reboost, operations and eventual deorbit depends on learning to take this quiet subtraction seriously. That is also why orbital decay so often disappears from popular imagination. Nothing on board feels like a steady wind. Nothing in the nightly sky announces that a calculation has become a little harder than it was last week. The evidence arrives through tracking and comparison. Altitude changes, planning changes, future burns have to be scheduled. In other words, the atmosphere reveals itself indirectly through the adjustments it keeps forcing on human beings. That indirect quality makes the problem quieter than most engineering problems on Earth. It does not make it smaller. If anything, it makes the station a better lesson in how serious systems live under conditions that have to be measured before they can be felt. Once drag is understood, the next question becomes unavoidable. If the station keeps losing orbital energy, how has it remained overhead for so many years? NASA answers that without any drama, periodic rocket firings boost the station's orbit. That line can sound like a routine footnote until you notice what it implies. The orbit we admire is not only the result of a successful launch long ago, it is the result of repeated later action. Reboost is a specialized word for a simple human idea. Something valuable keeps drifting away from the condition it needs. You measure the drift. You restore what has been lost. On Earth, the same logic keeps a reservoir full enough to operate or a heating system within range. In orbit, the quantity being restored is altitude and orbital energy. The correction does not need to be violent to matter. A careful push at the right time changes the station's future path. Left alone, the orbit will keep dropping. After reboost, the decline is interrupted and the station is returned to the altitude band where normal operations can continue. The public sees another smooth pass over the night sky. Behind that smoothness sits planned intervention. That is already a major change in how the ISS should be imagined. A structure that holds its place only because people keep acting on it belongs to a different category from a structure that can be forgotten for a decade with no consequence. The station has never lived in the second category. There is something useful in how unglamorous reboost sounds. Launch gets the movies. Reboost belongs to the quieter side of engineering culture. A burn window has to make sense. Vehicle capability matters. Crew safety matters. Station attitude matters. Other operations have to fit around it. Success looks almost invisible from the outside because the reward for doing the job well is that the station simply keeps being there. That invisibility can fool the mind. When maintenance is competent, people start calling it normal. Normal gradually turns into natural. The station orbits. Of course it orbits. It has always orbited. Reboost exposes how false that feeling is. The station remains there because people keep deciding that it should, and because they keep performing the work needed to make that decision real. NASA's broader material on the ISS helps here because it shows a living program rather than a dead object. There are crews, cargo flights, visiting spacecraft, experiments, repairs, and daily routines. Reboost is woven into that larger pattern. Orbit maintenance is not an isolated trick. It is one more system being managed inside a functioning outpost. That makes the station feel less like a monument and more like a utility network that happens to circle Earth. Most people using city water never see the pumps, they simply experience the result. The same thing happens with the station. Burns are planned, fuel margins are tracked, timing is chosen carefully. The public sees only another calm crossing above the horizon. For a moment that can sound reassuring. If Reboost works, maybe the whole issue reduces to willingness. Keep doing the burn, keep the station alive, keep the story going. The limitation appears as soon as you ask what Reboost actually fixes. It fixes one category of problem and fixes it well. Energy lost to drag can be restored. That matters enormously. What it does not do is erase every other burden tied to keeping a giant aging structure in low Earth orbit. Old hardware stays old. Debris risk remains part of the environment. Logistics still depend on vehicles, budgets, and institutions showing up on time. End-of-life responsibility still waits in the future. That is why Reboost is proof of control, not proof of forever. The distinction changes the emotional meaning of the station. A permanent object would hover above Earth like a monument. The ISS stays above Earth only as long as control remains available and worth exercising. That is an impressive fact. It is also a limiting fact. If you were on board after a successful boost, nothing in the immediate view would tell you a philosophical line had just been crossed. Earth would still roll past the windows. Work would continue. Meals would continue. The day would move on. Yet the station would once again have declared, through human action, that its orbit was something being managed rather than something granted. That is the hidden maintenance bill. Not one dramatic invoice arriving all at once, but a demand that keeps coming back and has to be met by coordination, fuel, and judgment. A homeowner can ignore such a bill for a while and then meet the consequences in the walls. An orbital program cannot ignore it at all. Reboost also reveals something about time. A roof on Earth may need repair only after years of weather. The station does not get that kind of pause. It keeps circling through the same physical problem on a schedule set by orbit itself. Operators can choose when to answer. They cannot choose whether the question exists. That is why Reboost belongs so close to the center of the documentary. It is the first place where the station admits, in plain operational language, that staying aloft is an active verb. So Reboost gives the first fully honest answer to why the station is still there. People keep putting back what the orbit keeps taking away. It also gives the first honest warning. Anything that stays aloft by repeated correction is telling you, in a calm technical voice, that its home is not naturally permanent. That is why Reboost should be imagined as scheduled upkeep rather than as rare rescue. It belongs to the same universe of thought as tightening a structure before vibration loosens it, or refilling a system before low pressure becomes failure. The station's teams do not wait for orbit to become a crisis before acting. They treat the gradual loss of altitude and energy as part of the environment itself. That attitude tells us something important about competence in space. Good operations are often boring from the outside because the response comes before the drama. Reboost is one of the clearest examples. It shows a program that does not pretend friction has disappeared. It simply keeps paying the price of living where friction still exists. That quiet professionalism extends outward through the whole support system around the station. A boost is never just one burst of thrust in isolation. It belongs to a larger operational ecology that includes traffic planning, vehicle support, crew schedules, and judgments about how to keep the platform useful without pretending utility comes free. That matters because it keeps the station from being romanticized as a lone object defying gravity through some timeless trick. The ISS remains there because many parts of a human system keep cooperating with a physical system that keeps asking to be answered. At this point, it can sound as if low Earth orbit was a bad choice from the start. If the atmosphere still matters there, if Reboost is required there, why build a station in that region at all? Because low orbit solves real problems even while it creates others. A station around 400 kilometers above Earth is close by spaceflight standards. That phrase matters. In ordinary life, 400 kilometers is not close at all. In orbital operations, it is the difference between an outpost that can be woven into a continuing program and one that remains a rare destination. Crews can reach this address without treating every visit as an expedition to the far deep. Cargo can follow them. Ground teams can build schedules, procedures, and rescue logic around repeated access, instead of hoping every major task succeeds on a single attempt. Closeness makes the station practical in the most literal sense. It keeps travel time, communications delay, and mission design inside a range that human organizations can support again and again. That changes the character of the whole project. A station at this height can become a place where people work, rotate out, receive supplies, install new equipment, and respond to failures before those failures grow into endings. Much of the station's value depends on that rhythm. Picture the alternative. Vernehmer, put the same laboratory much farther away, and every ordinary act becomes heavier. A crew exchange stops feeling routine. A cargo delay matters more. Maintenance turns into a rarer opportunity. Even the psychological meaning of the place changes. Instead of a destination that can remain in use, it starts to resemble an outpost that must justify each visit with unusual effort. The ISS did not end up in low orbit by accident. It ended up there because human beings wanted a laboratory that could be visited, supplied, repaired, upgraded, and inhabited over long stretches of time. That is the bargain. The useful address is not the permanent address. Low orbit is close enough to reach and close enough for the atmosphere to matter. Those are not separate facts. They are the two faces of the same choice. The station benefits from being where Earth can still support routine access. It also pays for being where Earth has not fully let go. Space engineering returns to that kind of compromise again and again. The most useful place for a mission is often not the cleanest place in theory. It is the place where the mission can actually be sustained. The station does not sit at the perfect height for permanence. It sits at a productive height for operation. We often imagine usefulness and longevity pointing in the same direction. In orbit, they can point against each other, and sometimes the wiser choice is the one that favors use over dreamlike endurance. If the station had been placed where routine access became far harder, many of the things that made it historically important would have weakened from the beginning. Long-duration research would be less routine. Crew life would feel more fragile. Repair opportunities would narrow. Another orbit might have been easier to imagine as permanent, but it would also have risked becoming less valuable day by day. The ISS chose the other kind of address. It chose the place where people could keep using it. NASA's Station Hub reinforces that reality by treating the ISS as a working platform, not a shrine. The public record is full of expeditions, experiments, dockings, cargo arrivals, and continuing operations. That is what low orbit purchased. It purchased repetition. It purchased the ability to turn one launch era into a long human presence above Earth. The price of that purchase was exposure to drag and everything that follows from living in a still busy layer of near space. This is why the question of forever is larger than sentiment. It is not only about whether people care enough to save a beloved object. It is about whether the operating address that made the object valuable can ever become timeless. The answer was built into the address from the start. Useful orbit is not timeless orbit. Think of a harbor. Ships stay there because a harbor offers access, shelter, trade, and movement. The same harbor also brings tides, corrosion, crowding, and continuous upkeep. Nobody calls a ship's berth permanent simply because the ship has returned to it for years. The value of the place is tied to traffic and maintenance. Low Earth orbit works like that on a larger scale. It is a working zone, not a museum shelf. That comparison helps with the emotional side of the problem. People feel attached to the station because it seems to have joined the sky the way an old ship joins a familiar waterfront. Affection can blur the physics. Harbors demand care because they are useful places. The station's orbit has demanded care for the same reason. Its value and its maintenance burden arrived together. That working zone quality becomes clearer when you remember how much the station actually does. It is not suspended above Earth as a symbol. People have lived there for long stretches. Science has been conducted there. Vehicles have arrived, departed, and docked with care. Repairs have taken place. Hardware has been replaced. Knowledge about life away from the ground has been accumulated there over years. A place with that kind of use must be reachable, and a reachable orbit keeps the station inside a region where maintenance never becomes optional. So low orbit was not a mistake hidden inside an otherwise great project. It was an honest operating choice. It gave human beings a place to build, visit, and learn. It never promised exemption from drag, and it never promised that one day the need for care would vanish. The station's success is inseparable from the compromise that now shapes its ending. This is why boosting the station forever is not a complete idea, even before we get to age or debris. The station was designed for ongoing work in a physically busy address. That is exactly what made it historically powerful. But a working address accumulates operational costs. It does not quietly transform into a permanent resting place just because the object there became famous. So low orbit should be seen neither as a mistake nor as a failure. It should be seen as the place where the station could become what it became. The fact that the same orbit also guarantees continuous intervention is not an irony added later. It is part of the original bargain. The station delivered decades of value because it lived in a place where humans could reach it often. The bill for that choice has been arriving ever since. Low orbit also allowed the station to remain experimentally alive in a way a more remote outpost might not have. When a new question emerged, the platform could stay part of the answer. Hardware could be delivered, components could be replaced, crews could keep cycling through with new skills and new research priorities. A farther station would not automatically lose all of that value, but the whole system would stiffen. More effort would go into simply reaching the place, which leaves less flexibility for everything learned after arrival. That practical flexibility is one reason the ISS became historically important. It was not only reachable once, it stayed reachable enough to remain useful. That practical closeness also shaped the station's emotional meaning on Earth. People could track it, visit it through missions that remained within a workable architecture, and treat it as an active place rather than a remote relic. Familiarity came from access. Access came from orbit. Orbit came with drag. The same choice that made the station part of regular human activity is the choice that now keeps the station inside a story about maintenance instead of permanence. The station's size changes the conversation in a way that is easy to miss. If the ISS were a small satellite, many end-of-life questions would become simpler. Smaller objects can still create problems, but they do not carry the same burden of control, visibility, and consequence. NASA describes the ISS as the largest human-made object ever to orbit Earth, with a mass of more than 400,000 kilograms. That figure matters even before it is translated into pounds. It tells us we are not talking about one tidy craft with one shell and one simple ending. We are talking about an assembled habitat. Pressurized modules form living and working spaces. The long truss carries major systems. Broad solar arrays and radiators give the station its unmistakable outline. Years of additions turned it into a place with structure spread across a wide frame rather than packed into a compact body. Mass matters because mass means momentum, energy, and responsibility. A giant object cannot be treated with the casual logic people sometimes use for smaller spacecraft. Lose control of something this large, and the scale of the public question changes at once. Final disposal also stops sounding simple. Nothing this massive comes home as one neat piece or one neat story. Mass also changes how much error society is willing to accept. A small re-entry object may still deserve attention, but a structure this large belongs to another level of planning. The margin for shrugging becomes smaller. The expectation of deliberate management becomes larger. Once the object is pictured clearly, end-of-life planning no longer feels optional. Shape matters almost as much as mass. The station has wide surfaces and delicate structures alongside dense equipment. Solar arrays exist for power. Radiators handle heat. Docking ports welcome arriving spacecraft. Pressurized modules hold people, air, water, experiments, and the systems that keep those things usable. That variety means different materials, different thicknesses, different thermal histories, and different responses once re-entry begins. Even without claiming exact breakup outcomes, one point is already clear: a station is not one object in the ordinary sense. It is a collection of very different parts, forced to share one fate. That is why scale turns a physics question into a public one. Drag and reboost are technical facts. A giant structure over Earth is also a matter of stewardship. The station is famous, its orbit is tracked, its operations are managed, its life is not anonymous. If a tiny fragment of forgotten hardware wanders through the sky, that is one kind of problem. If the most recognizable structure in orbit is allowed to drift toward an uncontrolled future, that is another. Size also changes the emotional meaning of neglect. When an object is small, forgetfulness can look harmless. When an object is massive, forgetfulness starts to look like policy. The station is too large to pretend that doing nothing would be neutral. It remains tied to ongoing human activity in orbit, and it remains tied to people below who did not volunteer to inherit unmanaged re-entry risk decades from now. There is a personal way to hear that. If a wrench slips from a mechanic's hand in a workshop, the event is local. If a bridge span over a city is left to fail on its own timetable, the event belongs to the public. The station's scale moves it much closer to the second example. Its fate is not private in any meaningful sense. There is another side to scale as well. The station's size is part of why it matters so much scientifically and historically. Its modules, power systems, and internal volume made long-duration life and research possible in ways smaller platforms could not match. The same enormity that complicates its ending is part of what made its operating life worthwhile. Greatness did not become a flaw. Greatness came with a final duty. The station's dimensions also make one common instinct harder to defend. If someone says, "Leave it there," the question that follows is simple. Leave what there? Not a symbol, not a dot. Leave a structure the size of a working outpost with all its exposure, all its hardware, all its future uncertainties, and all its potential to become somebody else's hazard later. Once the object is pictured clearly, leaving it alone stops sounding conservative. This is one reason NASA's deorbit planning uses the language of safe and responsible transition. Responsibility grows with scale. A large object asks for more from the people who built and operated it. It asks not only for maintenance during life, but for management at the end. The station's fame can make the final descent feel like loss. Its size should make the final descent feel like accountability. Imagine the difference between taking down a tent and dismantling a bridge. Both are structures. Both can be useful. Only one becomes a public risk if nobody plans its end. The station is closer to the second case. It is a bridge in the sky, and bridges do not become safer by being ignored once they are old. That is the real lesson of scale. The larger the object, the less plausible indefinite postponement becomes. Not because postponement is physically impossible in every moment, but because a giant structure multiplies every unanswered question. How long can it be trusted? How long can it be controlled? How long can partners keep supporting it? How long can future risk be pushed forward before pushing it forward becomes the irresponsible choice? A station this large does not just orbit Earth, it carries an obligation with it. Once mass and shape are both in view, another consequence becomes harder to ignore. A large station does not end as a single engineering calculation with a single public meaning. Every major surface and major subsystem changes how the object must be understood at the end of life. What was once a strength during operations becomes part of the closing burden. Wide arrays helped power the station. Large pressurized volume helped crews live and work there. External structure helped the whole platform grow over time. None of that becomes a mistake in hindsight. It simply means the same features that made the station capable also make its final handling a matter of deliberate public stewardship rather than casual disposal. Scale also changes how postponement feels. With a small object, delay can look harmless because the object itself barely occupies the public imagination. With the ISS, delay looks different. Too many people know what it is. Too much work went into it. Too many people below would inherit the consequences if the final phase were handled carelessly. That visibility is useful. It forces honesty. It keeps the end-of-life question in public language, where responsibility can be seen instead of hidden behind the false comfort of doing nothing for one more year. The station has been in orbit long enough for another kind of misunderstanding to set in. Survival starts to look like durability without cost. But years in orbit are not passive years. They are years of exposure. The station passes repeatedly from sunlight into darkness and back again. That means heating and cooling, expansion and contraction, daily cycles written into metal, seals, interfaces, coatings and joints. People on Earth know what time does to roads, buildings, machines and pipes even when they sit in ordinary neighborhoods. Orbit adds vacuum, radiation, thermal extremes, micrometeoroid risk, and the constant demand that life support and structural systems keep working inside a place humans cannot simply climb out of to inspect from all sides with a ladder. It is important not to drift into melodrama here. Age in orbit is not the same as a countdown to sudden failure. Large engineered systems can be extended, maintained, repaired, monitored and upgraded. The ISS itself is proof of that. Its continued usefulness for so many years shows how much careful work has gone into preserving it. But that is exactly the point. Continued usefulness has been earned, not passively granted. Think about what the station really is. It is not one shell, it is a network of shells and systems joined together. Hatches must seal, ports must align, structures must handle loads. Cabling and plumbing must keep serving hardware that supports life, power, cooling, experiments and communications. Solar arrays have their own history. Radiators have their own history. Docking systems have their own history. Every year of successful operation is also a year added to the maintenance story of a very complicated place. From the ground we speak of the station as if it were one object because that is how the eye receives it crossing the night. The engineering reality is closer to a small neighborhood linked by shared systems. Trust in that neighborhood depends on many parts remaining reliable together. That is one reason age matters even when no single failure is being dramatized. Complexity multiplies the number of judgments that have to stay good. This does not mean the station becomes unsafe the moment it is old. It means age cannot be wished away by the sentence "we have kept it going this long." That sentence sounds comforting, but it carries a hidden trap. Past success proves that control has been good. It does not prove that future control will always be equally available or equally wise to assume. Exposure to micrometeoroids and orbital debris adds another layer to that truth. Space is not packed like a road at rush hour, but it is also not empty in the way the human imagination prefers. Small natural particles and human-made debris move at extreme speeds. Shielding, tracking, procedures and careful operations reduce danger, but they do not abolish the environment. The station has spent years living inside that environment. Time in orbit is cumulative. Every additional year is one more year of thermal cycling, one more year of particle exposure, one more year in which careful management must continue succeeding. There is a useful distinction here between old and exhausted. A well-maintained machine can be old without being exhausted. The station has reached that state many times through labor, inspections, upgrades, and operational judgment. But the more years a machine accumulates, the less responsible it becomes to confuse old and indefinitely renewable. Every extension decision depends on continued evidence, continued support, and continued tolerance for what can go wrong. That is why age matters to our central question, even though age is not dramatic. The station cannot stay in orbit forever, not only because its orbit decays, but because the object itself keeps living through time. Its materials do not step outside history simply because they are above weather. In some ways, they enter a harsher version of weather. It helps to compare the station to a ship that never reaches dry dock in the ordinary sense. Crews keep living aboard, systems keep running, the route continues. Repairs happen, but the vessel remains in service and in environment at the same time. Eventually, the question is not whether the ship can be patched one more time. The question is whether the long chain of patching, monitoring, risk acceptance, and future obligation still adds up to the most responsible decision. That question does not insult the achievement, it honors it. A station that lasted only a few years could not force such careful judgment. The ISS does because it has done so much for so long. Its age is not a sign that the project failed. Its age is the reason the end-of-life decision has to be made like adults instead of romantics. The dream version of orbit imagines escape from erosion. The station teaches the opposite lesson. Orbit does not remove wear. It changes the forms of wear and spreads them across years that look serene from far away. The sun rises, the sun sets, the earth rolls underneath. The machine keeps its shape, and all the while, time keeps writing into the hardware. That is why old age in orbit has to be spoken of with respect rather than romance. Respect asks what inspections, repairs, replacements, and extensions have made continued operation possible. Romance asks only whether the image is still beautiful. The image is beautiful. The harder question is whether beauty should ever overrule the full accounting of exposure. It should not. That is why the station's final fate cannot be decided by altitude alone. A maintained orbit around Earth is one part of the story. A maintained structure inside that orbit is another. Forever has to win both arguments. No machine wins both forever. There is one more reason age matters here. Long service changes the kind of trust a machine needs. Early in life, operators ask whether the system can do what it was built to do. Later in life, they also ask whether the same system should keep doing it under the same assumptions. Those are different questions. The ISS answers the first one with extraordinary success. The second question is the one that pulls the story toward end-of-life planning. That is why extension should be heard as a judgment, not a spell. Extending a system does not make time reverse. It means people examined what time had done, decided what could still be trusted, and accepted the remaining obligations with open eyes. The ISS has benefited from that kind of judgment again and again. Yet every successful extension also proves the same deeper point. Continued service comes from evidence and labor, not from the station somehow escaping the ordinary rule that complex hardware accumulates history. Age becomes part of the mission record itself, and the mission record has to be read honestly if end-of-life decisions are going to make sense. That is part of what makes the station such a revealing machine. It has lasted long enough to show both human capability and human limits in the same frame. Capability is obvious in the way the platform kept serving crews and science across so many years. Limits appear in the fact that continued service always depended on renewed judgment. The lesson is not that time wins easily. The lesson is that time keeps asking the question again, and serious operators have to keep answering it with evidence. The station does not move through empty space in the ordinary sense. It moves through a region of Earth orbit that many human activities have found useful. That is another way of saying the address is crowded. Crowded does not mean packed bumper to bumper. Space still holds vast distances. What it means is that low Earth orbit contains many human-made objects, many useful altitudes, and many crossing paths that have to be watched with care. The station is not alone in a private lane. It shares a working environment with other missions, with hardware that still functions, and with fragments that no longer serve anyone yet still move at orbital speed. Once that is clear, debris stops sounding like a side topic and starts sounding like part of the station's ordinary life. Operators have to know what else is nearby, what might pass close, and when changing conditions deserve action. The issue is not that danger is constant in a theatrical sense. The issue is that awareness has to be constant. A region full of traffic asks for monitoring even on quiet days. This is why debris avoidance belongs in the same family as Reboost. Reboost answers drag, avoidance answers shared space. Both are forms of maintenance. Both only make sense once we stop imagining the station as something resting in perfect emptiness. Useful orbit is a managed environment, and management includes keeping the station away from other moving things when caution demands it. There is a human-scale way to hear this. Imagine living in a house that is safe and comfortable, but the road outside changes every day and some vehicles have no drivers. You can still live there, you can still do good work there, but part of the cost of living there is vigilance. Someone has to watch the road. The station's size makes vigilance even more important. A large structure presents area. Area matters whenever fast objects and close approaches matter. The solar arrays that power life and science widen the station's physical presence. The truss and modules that make it such a capable platform also make it impossible to picture as a tiny target. That does not mean the ISS is doomed by its own scale. It means the public burden of getting the end wrong becomes harder to excuse as the structure grows larger. Debris also changes the meaning of aging. An old structure in a quiet environment raises one kind of question. An old structure in a shared orbital neighborhood raises another. Even if nothing catastrophic happens, every additional year adds one more year of required confidence. The station must remain not only operable in itself, but safe inside a region where tracking, planning, and occasional avoidance remain part of ordinary life. It would be easy to turn this into a fear story, but that would miss the truth. The station is not one orbit away from disaster every day. That would be false and childish. The stronger point is calmer than that. A large, crude structure in low Earth orbit lives inside conditions that never stop asking for management. Drag keeps taking, shared traffic keeps changing, time keeps adding exposure. The station remains there because people keep answering those demands. There is a human consequence here that is easy to miss because all of this happens far overhead. Every avoidance judgment exists because people live inside the station. Every final disposal judgment exists because people live below it. The object ties those two kinds of responsibility together. That answer can be sustained for a long time. It has been. But the same facts that make the station admirable also make indefinite continuation harder to defend. Each extra year means more active management and one more year in which responsibility has been postponed rather than dissolved. This is also the point where a common reaction starts to surface. If low orbit is crowded and drag is persistent, then move the station somewhere else. Raise it higher, put it in a region with less atmosphere and perhaps fewer immediate burdens. That instinct is understandable. It sounds like a clean escape from the maintenance cycle. Yet the crowded highway leads directly to a harder question. Does moving a giant object upward solve the problem, or does it only move the deadline and change the form of the risk? It is one thing to maintain traffic and altitude while the station is an active program with active support. It is another to imagine that one more move could turn a managed, aging structure into a safely forgotten one. Higher altitude can delay some problems. It cannot make responsibility disappear. That distinction matters because traffic is not the only burden in view. A higher address would still leave the station large, old, and under somebody's responsibility. The real issue is not whether one pressure can be softened. The real issue is whether the full burden of stewardship has actually been solved. The station's environment has never been empty, and that is why its ending cannot be designed around absence. It has to be designed around control. Crowding also changes how patience works. In a remote wilderness, waiting may be neutral. In shared orbit, waiting is still a choice that carries background cost. Teams have to keep watching. They have to keep updating the picture. They have to remain ready to act if a path changes in a way that matters. That does not mean every day is a near miss. It means ordinary safety requires ordinary attention for as long as the station remains there. A crowded highway is not dangerous only when two cars almost touch. It is also demanding on every uneventful day because order itself has to be maintained. There is a useful moral shift hidden inside that picture. When the station was new, the public could mostly imagine risk as something the station itself might face. Over time, the question widens. Operators still have to protect the people inside, but they also have to think ahead to the people below who will one day inherit the consequences of every delayed end-of-life choice. A crowded orbit makes that widening unavoidable. Shared space means shared responsibility, and shared responsibility is exactly what makes controlled ending more honest than indefinite drift. Another quiet consequence follows from that. The better the station is managed in a crowded environment, the less dramatic the crowd appears from the outside. Success hides the traffic. It hides the judgment calls. It hides the daily act of not becoming a problem for something else and not letting something else become a problem for it. A managed environment often looks calm precisely because management is working. That hidden success matters when people imagine the station's future. If the public only notices danger when something nearly goes wrong, then years of uneventful management can create the illusion that management is barely needed. The opposite is closer to the truth. The long, quiet stretch is often the evidence that attention has been real and sustained. The most natural objection to everything we have said so far is also the most reasonable. If drag is part of the problem, why not move the station to a higher orbit where drag matters less? On first hearing, that sounds almost too sensible to argue with. Higher means thinner atmosphere. Thinner atmosphere means slower decay. Slower decay means less need for reboost. If the station already exists, why not give it a new address and buy more time? The first thing to say is that this is not a foolish question. It is exactly the question a practical mind should ask. But practical questions deserve complete answers. The station is not a small object that can be casually relocated. NASA's own numbers give us the right starting point. More than 400,000 kilograms, that is the anchor. A structure of that mass is not likely steered into a dramatically different future. Moving it higher in a meaningful way becomes a major act of propulsion, planning, risk management, and long-term consequence. Even without exact delta V figures, the logic is already strong. A small correction that maintains a working orbit is one thing. A major relocation meant to create a new long-duration future is another. Reboost keeps the station inside the conditions it was designed to operate within. A substantial move would ask older hardware, complex structure, support systems, and future planners to accept a new mission whose main purpose is no longer use. The main purpose becomes delay. That word matters. Postponement is not the same as resolution. Raising the station would not make it young again. It would not erase years of exposure. It would not remove the need to decide who remains responsible for it, who monitors it, who intervenes if something changes, and what plan exists when even the higher orbit is no longer the right answer. At best, a higher orbit might change the timetable and the kind of maintenance required. It would not create moral disappearance. There is also the question of what is being bought with that effort. A station farther away would not automatically become more useful just because it became harder to reach. One reason low orbit was chosen in the first place was that a laboratory there could stay woven into regular operations. Raise the station enough to escape some drag, and you begin trading against the same access that made the platform worth maintaining. There is also a subtle emotional trap hidden inside the phrase, "leave it higher." It treats the station as if its greatest value at the end of life would be existing somewhere, anywhere, rather than ending safely under command. But preservation is not automatically the same as care. Sometimes preserving a thing beyond the point of sound responsibility turns the appearance of respect into a way of avoiding a harder duty. That harder duty can feel emotionally wrong because it asks people to release a familiar object. Yet public safety often demands exactly that kind of maturity. The instinct to keep an old bridge standing or an old ship afloat can become dangerous if the future burden is quietly shifted onto strangers who only meet the object at the moment of failure. Orbit creates the same ethical problem, only farther from sight. Think of a bridge that has become expensive to inspect, expensive to repair, and increasingly uncertain over very long horizons. Hoisting it onto taller pillars would not solve the question of whether it should remain in service. Height can delay one class of problem while leaving the whole burden of ownership intact. The station faces a version of that logic in orbit. A higher orbit can also create a different temptation. Once drag becomes less immediate, it may become easier for future decision makers to let final disposal slide. The object is no longer decaying as quickly. The hazard feels distant. The budget pressure sits elsewhere. Responsibility drifts into later decades. Yet the station would still exist as a huge aging structure that eventually needs a controlled fate. Delaying the final decision can be useful when it creates a better decision. It is not automatically useful when it only creates a later one. This is why the station's planned ending is so revealing. NASA is not talking as if the responsible path were to push the ISS into a place where nobody has to think about it for a while. NASA is talking about safe and responsible deorbit in a controlled manner. That language tells us something important about how professionals in charge of the station understand the problem. The challenge is not simply to keep the object away from drag. The challenge is to bring a giant human-made structure through the end of life without shifting unnecessary risk onto people below or onto an undefined future. There is also a dignity in that answer. We often imagine technological seriousness as the refusal to let go. Sometimes technological seriousness is the opposite. It is the willingness to say that responsible systems have endings and that endings must be engineered as carefully as beginnings. So the phrase "just push it higher" sounds like rescue only if the real problem is pictured too narrowly. If the only issue were atmosphere, higher would look like escape. But the real issue is the whole chain together. Mass matters, age matters, operations matter, debris matters, ownership matters, long-term control and public risk matter. Against that full picture, higher is not rescue. It is one more choice inside the same moral landscape, and not the cleanest one. The station does not need a magical altitude. It needs a responsible conclusion. Another way to hear this is to separate engineering possibility from engineering wisdom. Many things are possible in stages. The real question is what kind of future a move is buying and what obligations come with that future. If a higher orbit only creates a more distant version of the same disposal question, then the move has to justify more than the pleasure of delay. It has to show that the extra effort truly leaves the public, the operators, and the future chain of responsibility in a better position. Otherwise, the move starts to look less like rescue and more like relocation of a burden. The access question belongs here too. Low orbit was never only a burden. It was also the condition that let the station remain woven into repeated human use. A higher orbit might soften one pressure while increasing another. Travel grows harder. Response can grow slower. The platform risks becoming less like a working laboratory and more like an object being kept alive, mainly because it already exists. That is not automatically impossible. It is simply a different mission, and a less convincing one if the core purpose has shifted from use to avoidance. Seen from that angle, higher orbit begins to look less like salvation and more like reclassification. The station would still be the same old structure, carrying the same history, just living under a different mix of burdens. Any honest defense of such a move would have to explain why that new mix was truly safer and more responsible, not merely later and less emotionally difficult. There is a moment in the life of many machines when maintenance stops meaning preservation and starts meaning postponement. The machine may still work, skilled people may still keep it working, but the reason for continuing has to be weighed against the burden of staying in control. That is the moment we are really approaching with the station. The station remains useful because people have cared for it well. It has supported research, crews, and long-duration human presence in orbit for years. Nothing about a planned ending erases that. In fact, the need for a planned ending grows out of the success of the project. Only something that has done a great deal over a long period forces such a serious final question. That point matters because public feeling often slips into the wrong grammar. A great machine is spoken of as if ending it means betraying it. But machines are not honored by asking them to carry burdens beyond the point where responsibility still adds up. They are honored by being used well, maintained honestly, and concluded without pretending that time has no claim on them. The wrong way to frame the issue is to ask why anyone would choose to destroy such an achievement. The better way is to ask what keeping it would require, for how long, and under what future uncertainties. Indefinite preservation is not one act. It is an endless chain of acts. Continuous control, continuous funding, continuous international cooperation, continuous confidence in old and aging systems, continuous acceptance that a giant structure remains above Earth because every generation after the builders decides to keep carrying the obligation. That is a heavier demand than it first appears. NASA's public language around the US. Deorbit vehicle is revealing here because it centers risk to populated areas. That phrase points to the real fear. The danger is not that engineers plan a descent. The danger is the possibility that a huge aging object could one day descend without adequate planning, or remain aloft until options narrow, or shift a preventable burden onto people who had nothing to do with its creation. Controlled deorbit is the attempt to prevent that future. Put differently, the worst version of the station's end is not a planned return. The worst version is a future in which the object still exists overhead, still carries great mass, still carries aging hardware, and does so at a moment when the power to guide it has become weaker than it once was. Waiting can feel careful. Sometimes waiting is merely leaving tomorrow with fewer good choices than today. This is the reversal that responsible control demands. The fall itself is not the irresponsible part. The responsible part is making sure the fall happens under command. We can put the point very simply. A station this large will not become harmless because people stop making decisions about it. It will become more dependent on the quality of decisions already made and the quality of decisions still delayed. If a structure must eventually leave orbit, then the safest version of that event is usually the one planned while control is still strong. There is a temptation, especially with beloved machines, to treat continued existence as the highest value. But existence is not the only value. Reliability matters, control matters, public safety matters, honesty about aging matters, responsibility for the full life cycle matters. If those values start pointing toward an engineered ending, then refusing the ending is not automatically the noble path. You can hear this on Earth wherever large systems outlive the first era of enthusiasm around them. The first question is always whether something can be built. The second is whether it can be run. The final question is whether it can be retired without denial. The station has already answered the first two brilliantly. The third answer is now part of its legacy. In some ways, the station resembles a very large industrial site built in a difficult place. As long as teams can monitor it, service it, supply it, and trust its essential systems, operation can continue. Eventually, the question changes. The question becomes how to retire the site in a way that protects the public and respects the reality that no operating system remains indefinitely immune to time. Proper closure becomes part of proper operation. That is the grown-up lesson hiding under all the orbital mechanics. Human achievements are not diminished by careful endings. They are diminished when we refuse to plan their endings because we confuse sentiment with duty. The ISS forces that lesson into view because it is so visible and so beloved. It is harder to tell comforting myths about a giant structure everyone recognizes. If the most famous station in history still needs a managed final descent, then orbit itself has made its point. Keeping something in low Earth orbit is never just a matter of affection. It is a matter of continuous competence and eventually of choosing the safest time to stop. So when preservation becomes a risk, the meaning of care changes. Care is no longer measured only by how long the object remains where it is. Care is measured by whether those in charge are willing to guide it through the last part of its life, before control becomes more fragile than it should be. That is why the station must fall. Not because it failed, not because it lost all value, but because a responsible civilization does not wait for a giant aging structure to make the end-of-life decision on its own. That transfer of obligation matters, because the station is not owned by sentiment alone. It is tied to institutions, budgets, partnerships, crews, and public risk responsibilities that have to remain real long after any one moment of affection. Keeping a machine overhead for one more year is easy to say in the abstract. In practice, it means somebody must still be prepared to watch it, guide it, maintain it, and finally bring it down safely when the time comes. The longer that chain is extended, the more carefully it has to be justified. Otherwise, preservation slowly stops being care and becomes avoidance. That is why responsible timing matters so much. A controlled end is easiest to defend when options are still broad, when cooperation is still functioning, and when the means of control are still strong. Wait too long, and the same decision may have to be made under weaker conditions. The station's story keeps pushing toward that adult truth. Responsibility is not only about choosing the right act, it is also about choosing it before delay has turned prudence into wishful thinking. That is the point where timing and honesty start to merge. A mission can honor its own achievement by ending before its chain of control has to be stretched into a weaker future. Waiting is not always caution. Sometimes it is only reluctance wearing the language of caution. The ISS has become important enough that its ending deserves better than reluctance. Controlled deorbit sounds dramatic when it is reduced to 2 words. In practice, it means something more careful and more modest than many people assume. It does not mean commanding every fragment with perfect certainty. It does not mean turning Reentry into a neat theatrical scene. It means choosing the timing and path of the descent as far as physics, engineering, and uncertainty allow, so that the remaining risk is pushed away from people as much as possible. That is an important distinction. The station is not a paper airplane that can be flown to a point on a map. Reentry is violent. Heating rises. Structures break apart. Different materials behave differently. A giant object does not remain one thing all the way down. Control in this context means shaping conditions, not abolishing uncertainty. The easiest way to hear the difference is to compare 2 kinds of fall. In the first kind, an object loses control, and the world waits to see where and when it comes down. In the second kind, people still have authority over the timing, the orbital path, and the overall plan, so the inevitable descent is guided into the least harmful conditions available. Both involve falling, only one involves stewardship. This is where the idea of a corridor becomes useful, even without overstating technical details. A planned re-entry is not about one exact point. It is about choosing a broad path and a broad outcome region that minimize public risk. The goal is not cinematic precision. The goal is disciplined uncertainty management. If some debris may survive, then the responsible act is to shape where that possibility is concentrated. Remote ocean targeting is the human translation of that idea. The aim is not to make the station disappear into a fairy tale, but to keep the remaining uncertainty far from the dense patterns of ordinary life. Cities, towns, farms, roads, ports, and flight routes all represent concentrations of people who never agreed to absorb avoidable risk from a machine finishing its mission. The farther uncertainty is moved from those patterns, the more honest the plan becomes. This is why control at the end should be judged by intention rather than fantasy. A good plan does not promise that nature becomes tidy. A good plan promises that known danger is pushed away from where it would do the most harm. That is a very human kind of responsibility. It begins by admitting that some parts of reality remain messy, and then it asks what can still be shaped before the event arrives. That sentence sounds cold until it is translated into ordinary life. Imagine knowing that a large structure must be dismantled and some material might scatter. One option is to let the structure fail when and where it happens to fail. Another is to bring it down in a remote place under prepared conditions. Even if you cannot predict every fragment, the second option is plainly safer. That is what controlled deorbit means at heart. NASA's language about avoiding risk to populated areas tells us that this public safety logic is central, not secondary. The station's descent is not being planned as a spectacle or as a symbolic ending. It is being planned as risk reduction. That public safety language is worth lingering on because it changes the emotional framing of everything. Once the question becomes risk to populated areas, the station is no longer only a beloved object above the world, it is also a future event that must be arranged in a way that respects people below who may never have thought about it at all. The last obligation of the mission extends outward to them. In that sense, controlled deorbit is one of the clearest examples of engineering humility. It does not say, "Trust us, nothing complicated will happen." It says, "Complicated things may happen, and because of that we are using the control we still have to protect strangers who never asked to become part of this mission." Humility like that is often quieter than triumph, but it is one of the marks of serious technical culture. This also explains why uncertainty strengthens the case for control rather than weakening it. If breakup and debris behavior cannot be known with total certainty, then leaving a giant object to a less controlled future becomes harder to defend, not easier. Uncertainty is not an excuse to avoid planning. It is the reason planning matters so much. There is a broader philosophical lesson here too. People often treat control and uncertainty as opposites. In real engineering, they live together. Good control does not require perfect prediction. It requires honest limits, disciplined models, margins, and decisions made before events outrun the ability to shape them. Controlled deorbit is exactly that kind of act. It accepts that the atmosphere, heating, breakup, and surviving fragments cannot be fully written down in advance. Then it uses the control still available to reduce the harm that uncertainty could otherwise spread. The station teaches this lesson beautifully because the word fall is so easy to misunderstand. In ordinary speech, falling suggests failure, accident, or surrender. In orbital life, a planned fall can be the final proof that responsibility is still active. Aimed descent is not the opposite of achievement. It is often the last act of competent achievement. That is why a controlled return should be pictured less like collapse and more like the final steering input on a long mission. The object is coming down either way once its life in low Earth orbit ends. The real issue is whether that return happens while care still has force. That is the difference between guided closure and passive drift. If someone on the ground never learns any of the detailed mechanics, that distinction should still be enough. The station is not being aimed because humans enjoy destroying what they built. It is being aimed because a planned descent is gentler to the public than an unmanaged one. The final command is not impatience, it is protection. That is why the station's ending should not be imagined as the moment humanity loses control of a great machine. It should be imagined as the moment humanity uses the last control it has for the purpose that matters most at the end, reducing danger for people below while bringing a long mission to an honest close. If a structure must come home, being aimed is everything. That is also why remote ocean language matters so much in official discussions. The point is not to create a dramatic destination. The point is to move unavoidable uncertainty toward places where far fewer people would be exposed to it. In that sense, a controlled deorbit corridor is a moral geometry. It uses what control remains to shape who bears the risk and who does not. That is a much more serious idea than the casual phrase falling out of orbit suggests. That makes the distinction between aimed and unmanaged return easier to hear in ordinary terms. One path keeps human judgment present until the last broad decisions have been made. The other path leaves more of the final geometry to chance and delay. Both paths eventually meet gravity and atmosphere. Only one of them treats the people below as the central fact in the calculation. That is why the language of control matters so much. It is not a technical ornament. It is the ethical content of the whole maneuver. This is why controlled deorbit belongs to the language of public protection rather than the language of spectacle. If the station were tiny, the distinction might feel remote. Because it is large, the distinction becomes central. Aimed descent says that the final phase of the mission still answers to people on Earth, and not only to the inertia of an aging object. That is the quiet dignity of the idea. The station is not being left to explain itself through whatever descent happens to occur. Its operators are still speaking for it through guidance, timing, and deliberate choice. Even the last fall remains an act of stewardship. By the time we reach the dedicated deorbit vehicle, The logic for its existence should already feel obvious. The station's end is not just another reboost. It is not one more maintenance burn added to an old routine. It is a final act that has to manage the descent of the largest human-made object ever placed in orbit, while avoiding risk to populated areas as much as possible. That requires a level of end-of-life control that ordinary routine operations were never meant to carry forever. One way to hear the difference is to compare a tune-up with decommissioning. During life, the station has needed repeated help so that work could continue. At the end, the goal changes. The purpose is no longer to extend ordinary operations by a little more time. The purpose is to carry the whole structure through a safe conclusion, while the power to guide it still exists. NASA's announcement about the US deorbit vehicle tells the story in deliberately sober terms. NASA selected SpaceX to develop and deliver the vehicle. NASA says the vehicle is intended to provide the capability to deorbit the station and avoid risk to populated areas. After development, NASA will take ownership and operate it during the mission. The deorbit vehicle is expected to break up destructively with the station during re-entry. Every part of that description is instructive. First, the fact that a dedicated capability is being created tells us that the final descent is not being treated as an afterthought. The station has had visiting vehicles and reboost support during its life, but end-of-life disposal for an object this large is its own engineering problem. Final control is not something to improvise because the need happens to arrive. It is something to prepare. Second, the language about avoiding risk to populated areas confirms again what the core issue is. The station's ending is not framed as clearing clutter from space or making room for the future. It is framed as a duty to manage a giant object's return safely and responsibly. Public safety is not a side note, it is the spine. Third, the fact that NASA takes ownership and operates the vehicle during the mission matters because it keeps the story from collapsing into brand drama. The name of a contractor is less important than the structure of responsibility. This is still a NASA mission at the level that counts. The vehicle exists to serve a controlled public safety objective for an internationally operated station at the end of its life. That structure of responsibility is easy to overlook in a culture trained to chase headlines, yet it is one of the most reassuring parts of the whole plan. The final descent is not being treated as a loose commercial handoff. It remains an institutional obligation with public consequences. That is exactly how something this large should end. That keeps the focus exactly where it should be. The important thing is not the contractor's spotlight or the novelty of another spacecraft. The important thing is that the station's last major command will have a tool designed for that purpose. There is something powerful in the fact that the vehicle is expected to end with the station. It is not a tug that moves the ISS to a safer shelf and then drives away to a second career. It is a purpose-built partner for the final descent. That gives the whole plan an unusual moral clarity. This is not prolongation disguised as care. It is care expressed as conclusion. There is something fitting about that. The station spent its life depending on arrivals. Crews came aboard. Supplies followed. New hardware joined the structure over time. The last crucial arrival serves a different purpose. It is there not to continue the familiar rhythm, but to end that rhythm without surrendering control. The final visiting craft carries closure. You can almost think of the deorbit vehicle as the last missing sentence in a long engineering paragraph. Early sentences described launch and assembly. Later ones described docking, habitation, research, maintenance, and extension. The last sentence has to explain how control remains real when gravity and atmosphere begin doing their irreversible work. The vehicle exists to make sure that final sentence is written by people, not by neglect. The presence of the vehicle also rebukes one common fantasy. People often imagine that a structure in orbit can simply be left alone until nature takes over. But nature taking over is exactly what professional operators are trying to prevent from happening in an uncontrolled way. The vehicle is the proof. If doing nothing were responsible, there would be no need to create a specific capability for the ending. A good ending tool can teach as much as a beginning tool. Rockets teach us what it takes to lift mass into orbit. A deorbit vehicle teaches us what it takes to bring a massive structure out of orbit responsibly. One machine announces ambition, the other announces maturity. The second can be harder for a culture to admire because it looks less triumphant. Yet it shows a harder kind of seriousness, the seriousness that thinks all the way to the last public consequence. The station could only become what it became because people kept extending control into a hostile place. The deorbit vehicle continues that tradition all the way to the end. It says that the mission does not stop being engineered when the mission stops being useful in its old way. It remains engineered until the risk has been carried back down under human command. That is why the final control vehicle belongs late in this story. It only makes sense once the need has been earned. Now it has. Prepared final control matters for another reason as well. It changes the station's last phase from an improvisation into a mission with its own integrity. The engineers do not simply hope that ordinary operations can stretch one last time into an ending task they were never built around. They acknowledge that the last maneuver deserves its own hardware and its own plan. That is a mature way of speaking about large systems. A beginning this ambitious required special machinery. An ending this consequential requires special machinery too. The symmetry tells us that the mission is being respected from first launch all the way to last command. The vehicle also signals something about institutional memory. NASA is not acting as if the station's last phase can be improvised out of leftover habits from earlier years. Instead, it is marking the ending as a separate operational problem that deserves focused design. That matters because large systems often fail at the edges of their own history when people assume the last task will resemble the earlier ones enough to reuse the same thinking. The deorbit vehicle is evidence that this assumption is not being allowed to stand. In that sense, the deorbit vehicle is almost a statement of values made in hardware. It says the last phase will not be left to improvisation, optimism, or hand-me-down assumptions from earlier operations. It says the station will receive a deliberate closing tool, because deliberate closing is part of responsible spaceflight. The word reentry can invite bad imagination. Many people picture one giant object turning into one giant fireball and then vanishing, or else surviving intact until the last moment. Neither picture is right. Part of the reason those pictures survive is that they satisfy opposite emotional needs. One makes the problem disappear too neatly, the other turns it into total drama. Reality is less comfortable and more manageable than either extreme. Reentry is messy enough to require caution and structured enough to justify planning. Reentry is a process. Heating rises, forces rise, structures encounter conditions they were never meant to survive indefinitely. Different parts respond in different ways. Thin pieces can fail early. Dense pieces may behave differently. Wide structures do not meet the air the same way compact ones do. That is why the ending has to be discussed in terms of models, planning, and uncertainty, rather than in terms of a movie scene. NASA's public materials point to re-entry and debris work as a dedicated field for a reason. Predicting what survives and where it may fall is not a matter of storytelling instinct. It is a matter of disciplined analysis, and disciplined analysis includes limits. That is why exact fragment counts, exact breakup details, and exact footprint claims should be handled cautiously. Still, caution does not leave us knowing nothing. We know enough to understand the shape of the responsibility. A station this large will not simply wink out as if the atmosphere were an eraser. Re-entry planning has to assume that the object is complex, that breakup is dynamic, and that some surviving debris may remain part of the risk picture. That is why a footprint matters. A footprint is not a point. It is the region where surviving debris could come down. The idea is easier to understand if we refuse the wrong picture. Imagine smashing a ceramic plate from high above. The pieces do not all choose one square on the floor. They scatter across an area. Controlled deorbit planning treats the station's descent with far more sophistication than that simple image. but the basic lesson is similar. Risk is spread across space. Good planning tries to place that spread where it is least dangerous. That matters in human terms because people live in patterns, not in abstract maps. Populations cluster, shipping lanes cluster, aircraft routes cluster, infrastructure clusters. A region with few people is not morally identical to a region full of them. When planners shape the broad geometry of a re-entry, they are really shaping who is asked to bear the remaining uncertainty. Good planning tries very hard to make that answer as close to nobody as possible. This is why the phrase aimed matters more than people first realize. No one is promising to command every fragment. What professionals are trying to command is the large geometry of the event. They choose timing, they choose path, they choose the broad conditions of descent and the broad relationship between uncertainty and population. Control lives at that level. That can sound less satisfying than perfect certainty, but it is how most serious risk management works. A dam is not secure because every molecule of water can be told where to go. A storm warning is not useful because every raindrop can be tracked. Safety often comes from shaping the large outcome while admitting that details remain probabilistic. Re-entry is one of those domains. There is also a moral clarity hidden in this uncertainty. If exact breakup details cannot be known ahead of time with total confidence, then waiting for a future uncontrolled descent becomes even less responsible. Uncertainty is not a reason to shrug, it is a reason to act while guidance is still possible. The station teaches a very modern lesson here. Advanced technology does not remove uncertainty from the world. It often increases our power to manage uncertainty responsibly. Controlled deorbit is not the fantasy of perfect command, it is the practice of using imperfect command in the wisest available way. There is a strange comfort in that once it is faced directly, the station does not need impossible promises from its final descent. It needs honest promises. We will model carefully. We will choose conditions carefully. We will place risk carefully. We will not pretend away the parts that remain uncertain. That is the voice of serious stewardship. That makes the final descent less like an accident and more like a carefully bounded surrender to realities that were always there. Atmosphere was always there. Heating was always waiting below. Material limits were always part of the station's future. The only real question was whether the return through those realities would happen under plan or without one. If you listen carefully, that is the whole argument of the documentary in another form. The station cannot stay in orbit forever because low Earth orbit was never outside process. Drag is a process. Aging is a process. Debris risk is a process. Re-entry is a process. The station's life has been a long conversation with processes. Its ending is the last and most public one. So what can re-entry promise? It cannot promise a miracle. It cannot promise total disappearance. It cannot promise absolute precision. What it can promise is quieter and more serious than that. It can promise that a giant human-made structure will be brought down with planning, with professional restraint, and with public risk treated as the thing that matters most at the end. The discipline behind that planning can sound almost cold until you picture the alternative. Without models, without corridor logic, and without a dedicated effort to bound uncertainty, a huge object would still meet the atmosphere one day. Physics would not wait for better feelings. Careful re-entry work is how human judgment stays present inside an event that cannot be made perfectly predictable. The station does not need mythology at that stage. It needs modesty, modeling, and a plan strong enough to carry uncertainty without pretending it has vanished. That is why sober language is a form of respect here. If the end of the station were described as either total disappearance or cinematic destruction, the real planning problem would be hidden under a false picture. Engineers need a truer picture than that. They need to think in ranges, conditions, models, and residual risk. Public trust deserves the same honesty. A giant object can be brought down responsibly without anyone pretending that responsibility means omniscience. In fact, responsible planning begins by admitting where exact foresight stops. That modesty is one reason controlled re-entry deserves more respect than a fantasy of perfect prediction. Serious planning does not deny uncertainty. It works around uncertainty with enough discipline to make the broad outcome safer. A giant object does not become harmless because every detail is known. It becomes safer because the important unknowns are carried inside a plan built to contain them. That is the difference between mature uncertainty and careless uncertainty. Mature uncertainty is measured, bounded, and steered. Careless uncertainty is simply inherited after someone postponed a decision. Re-entry planning exists so the station can end under the first kind rather than the second. The ISS is not the first large object in orbit to force people to think about descent, public attention, and responsibility. That history matters, but it must be used carefully. We are not starting a second documentary here, we are looking for contrast. One kind of contrast comes from Mir. In the approved source package, Mir appears as the precedent for a controlled station descent. That alone matters. It reminds us that deliberately bringing down a large space station is not an unimaginable act invented just for the ISS. There is history behind the idea that a long-lived station can end under command rather than by drift and hope. Mir also helps restore proportion. Once people remember that a station can be guided through a final descent, the act itself stops feeling like sacrilege. It becomes part of the known grammar of orbital responsibility. A station can be loved, studied, and historically important, while still requiring a deliberate return through the atmosphere at the end of its life. Mir's example helps normalize the core concept. Great orbital structures do not become sacred ruins that must remain above Earth forever. They can complete their operating life and still require a managed ending. Control at the end is part of the same civilization that built them. Another kind of contrast comes from Skylab. In public memory, Skylab represents something else, the anxiety and spectacle that surround an uncontrolled return. Even people who know little about orbital mechanics have heard the basic story that pieces might come down and that the timing was uncertain enough to become global conversation. That memory matters because it shows how differently the public experiences descent when the dominant feeling is waiting rather than steering. What people often remember in such cases is not a technical table of details. They remember the uncertainty itself. They remember that geography became suspense. That kind of memory matters because it reveals what public confidence feels like when control is weak or absent. The ISS should not have to end inside that emotional register if a more disciplined route remains available. A later example like Tiangong 1 sharpens the same point from a more recent era. Public tracking, public uncertainty, public fascination with where and when something might come down. The scale was not the same as the ISS, and the comparison should not be abused, but the pattern is useful. When an object re-enters without the same degree of planned final control, public attention fills the gap with prediction, worry, countdowns, and scattered guesses. Those moments reveal something about technology and trust. People can live comfortably with complex machines when they believe someone remains in charge. When that confidence weakens, even low probabilities start to feel louder. The station's operators are trying to avoid that exact atmosphere of public waiting and guessing. Those moments reveal something about technology and trust. People can live comfortably with complex machines when they believe someone remains in charge. When that confidence weakens, even low probabilities start to feel louder. The station's operators are trying to avoid that exact atmosphere of public waiting and guessing. What these historical examples really teach is not that every return becomes disaster. They teach that control changes the social meaning of descent. A controlled return is a management problem. An uncontrolled return becomes a guessing problem for everyone watching. The bigger the object and the higher the visibility, the less dignified that guessing becomes. This is why historical parallels strengthen the case for the station's planned ending. They give us a memory of alternatives. One alternative is deliberate disposal. Another is public uncertainty. If a structure is famous, massive, and still under active institutional authority, Choosing the second when the first remains available would be difficult to defend. There is also a cultural lesson hidden here. Human beings are strangely vulnerable to the romance of relics. We like to imagine old achievements lingering. A station in the sky can feel like a monument that honors itself by remaining visible forever. Historical returns push against that romance. They remind us that machines in orbit are not statues in a museum courtyard. They obey trajectories, heat, drag, and material limits, whether we project symbolism onto them or not. Mir, Skylab, and Tiangong-1 matter not because their details are identical to the ISS, but because together they outline the space of possibilities. Large objects do return. Some returns are controlled, some are much less so. Public memory treats those categories very differently because public risk is not the same in each case. That is useful for one more reason. History keeps this conversation from becoming too sentimental or too abstract. Once other stations and large orbital objects are remembered, the ISS stops looking like a special exception that deserves a fairy tale ending. It returns to the category it always belonged to, a major human-made structure that must eventually pass back through the same physical world it once seemed to escape. That historical memory should make the station's planned future easier to understand. A controlled descent is not a shocking betrayal of what a station is. It is one recognized path by which a station's life can be completed responsibly. The shock belongs more properly to the idea of refusing to plan when planning is still possible. And there is one final reason these comparisons matter. They pull the ISS out of the realm of exceptional sentiment and place it back into the realm of engineering history. The station is extraordinary, but it is not exempt from the larger rule. Human-made things in orbit eventually meet the atmosphere again. The only real choice is whether they meet it with guidance or by default. That is the kind of lesson history gives when it is used well. Not nostalgia, not fear, orientation. Those older returns also correct our emotional scale. Public memory often compresses them into headlines, rumors, and a few surviving images. Engineers, though, remember them as different kinds of end-of-life management with different kinds of public risk. That is the useful lesson for the ISS. History does not merely tell us that objects come down. It tells us that the manner of return changes how responsibly a mission finishes its life. Control, or the lack of it, becomes part of the meaning of the event itself. Memory matters because it trains public instinct. People who remember uncontrolled returns remember uncertainty, speculation, and the uneasy feeling of waiting for physics to finish a story without much guidance. People who remember controlled returns remember something else. They remember that large objects can be brought down as part of a plan instead of as a late surprise. The ISS belongs in that second tradition if its life is going to remain consistent with the seriousness that sustained it. History also keeps the ISS from being trapped inside its own fame. The station is extraordinary, but it is still part of a larger class of orbital machines that eventually have to come home in one way or another. That recognition is healthy. It prevents reverence from turning into exemption and keeps the discussion tied to engineering reality. History gives the station perspective, and perspective is one form of honesty. It reminds us that endings are part of the craft, not exceptions to it. That is the healthier memory to keep. It would be easy to end with the ISS alone, as if its descent were the final page of a special era and not a lesson for whatever comes next. But the station matters precisely because it is not only about itself. NASA's broader framing around the station includes transition, continuing low Earth orbit activity, and the future of orbital infrastructure. It would be a mistake to let that turn this into a policy argument about replacements. The important point is simpler. Whatever stations come next will inherit the same categories of responsibility, even if their designs, owners, and missions differ. A future station could be smaller than the ISS. It could be privately operated, it could be assembled in a different way or aimed at a different mix of work. Perhaps it supports research, perhaps it supports manufacturing, tourism, or other missions not yet routine. None of that lets it escape the logic we have been tracing. If it lives in low Earth orbit, drag remains part of the picture. If it is large and complex, age remains part of the picture. If it occupies shared orbital space, debris and traffic remain part of the picture. If it survives long enough to matter, disposal remains part of the picture. Newer projects may need this lesson even more because novelty encourages optimism. Fresh hardware feels clean, new architecture feels agile, new ownership models feel like resets. Physics does not care. A new station still meets thin air, high speed, exposure, traffic, and eventual retirement. The invoice simply arrives later, after enough years have passed for the structure to look familiar and for people to forget that the bill was always coming. That is why end-of-life planning should not be treated as a depressing appendix written after the exciting design work is done. It belongs near the beginning. The ISS, alone, as if its descent were the final page of a special era and not a lesson for whatever comes next. But the station matters precisely because it is not only about itself. If a future station cannot explain how it will be maintained, how it will avoid burdening the public, and how it will eventually leave orbit responsibly, then part of its design remains morally incomplete, no matter how elegant the structure looks in early presentations. That means the ISS is not only ending, it is teaching. One of the great temptations in frontier technology is to fall in love with beginnings. New stations arrive with drawings, launches, investors, and bold promises. Beginnings are easy to advertise. Endings are harder because endings force honesty. They reveal whether an industry or a civilization understood the full life cycle of its own ambitions. The ISS makes that honesty unavoidable. Future builders can admire the station's scientific legacy, its international legacy, and its engineering legacy. They should also study its maintenance legacy and its end-of-life legacy. The real question for a future platform is not only how well it can be built or how long it can be occupied. The deeper question is whether the plan for keeping it safe, useful, and ultimately disposable is present from the start. In ordinary engineering on Earth, that idea is familiar. Bridges, reactors, aircraft, and industrial sites are not judged only by performance during their best years. They are judged by inspection regimes, maintenance plans, retirement logic, and the seriousness of decommissioning. Space infrastructure is growing up into the same standard. The station's planned controlled end is part of that maturation. There is even a strategic comfort in this. The need for end-of-life planning does not mean human work in orbit is fragile or doomed. It means orbital work is becoming mature enough to include closure in its design vocabulary. A child thinks only about building the treehouse. An adult also thinks about how the wood ages and what happens when it must come down safely. This is why the station's fate should not be filed under sad necessity and then forgotten. It should be treated as one of the most valuable lessons the ISS can still give. Orbit was never free to use without upkeep. The structure was never free to keep without judgment. The ending will not be free of planning either. Every station after this one will face the same truth, even if the numbers and schedules change. So the real inheritance is not just hardware knowledge or life support experience or international operating practice. The inheritance is ethical. Build in orbit and you accept the full arc. You raise a structure, maintain it, protect it, and one day remove it responsibly. That is a stern lesson, but it is also a hopeful one. It means we are capable of treating space not as a place where consequences disappear, but as a place where consequences must be met with better planning. Future stations do not inherit a curse. They inherit a standard. For anyone who hopes human activity in orbit will grow rather than shrink, that standard should be welcome. Expansion without retirement logic is not maturity. Expansion with maintenance logic, disposal planning, and public risk discipline is maturity. In that sense, the station's ending may become one of its clearest gifts to what comes next. The most useful future for orbit is not one in which every structure stays up, as long as sentiment can defend it. The most useful future is one in which builders know, from the first sketch onward, that staying aloft and coming down safely are both parts of the same responsibility. The ISS is making that lesson harder to ignore than any abstract policy paper ever could. And the ISS, by making that standard vivid, may end up serving those future stations even in the act of leaving the sky. That is why future stations should be designed with retirement in mind, long before anyone is tempted to call retirement pessimistic. A platform that intends to live in orbit for years is already making a promise to the public. The promise is not only that it will do worthwhile work. The promise is that its builders understand the full arc of responsibility that worthwhile work creates. If retirement logic appears only after a structure becomes famous, then part of the design thinking arrived too late. The ISS is teaching future builders to move that thinking forward. This is one reason the ISS should matter to future orbital businesses and future public programs alike. It demonstrates that end-of-life discipline is not a bureaucratic footnote added by cautious people after the exciting work is over. It is one of the exciting questions if the project is mature enough to see itself clearly. Building something that lasts in orbit is impressive. Building something that can end without leaving confusion and unmanaged risk behind may be just as impressive, even if it is harder to market in a headline. That is why life cycle thinking should be counted as part of ambition, not as its opposite. A civilization that can imagine new orbital habitats should also be able to imagine their safe retirement from the start. The ISS is forcing that maturity into the foreground, and future projects will be stronger if they accept the lesson early rather than learning it late. Return to the first image, the station crossing above the blue edge, bright solar arrays, dark truss, Earth rolling underneath. From far away, it still looks calm enough to call permanent. But now the picture has changed. The station is no longer just a heroic object suspended above the planet. It is a machine moving through the highest traces of the atmosphere and losing orbital energy a little at a time. Its path has been corrected again and again through Reboost. It became a working laboratory by living in an orbit that could be reached and serviced, which also meant living in an orbit that could never be entirely free of Earth's influence. Scale belongs in that picture too. The ISS is the largest human-made object ever to orbit Earth. Age belongs there as well. The station has lived through sunlight, shadow, time, and risk. Shared orbital traffic belongs there. So does the need for tracking and avoidance. The old still image hid all of that. The corrected image keeps all of it in view at once. That long chain matters because no single fact alone forces the ending. Drag by itself does not explain everything. Age by itself does not explain everything. Debris by itself does not explain everything. Even the existence of a final deorbit vehicle does not explain everything. The answer lies in the way all of those facts lock together. Low Earth orbit keeps taking a little energy, and Reboost keeps restoring it. Reachable altitude made the station useful, yet that same reachable altitude left the station inside the problem of drag. Great scale made the platform historically powerful, yet the same scale made a future uncontrolled end harder to tolerate. Long life proved engineering excellence, but long life also meant prolonged exposure and prolonged obligation. Public risk at the end did not appear out of nowhere. It was the final consequence of keeping a vast structure aloft in a place that was never permanent storage. That chain can be heard in ordinary terms as well. If a family keeps an old house standing through patient care, the house is not immortal. If a town keeps an old dam safe through inspection, the dam is not immortal. Success in maintenance proves devotion and skill. It does not repeal material limits. The station belongs to that same class of honest achievements, only set against Earth instead of on its surface. What changed over the course of this question was never the object alone. The station at the end of the discussion is still the station from the opening image, with the same arrays and the same modules crossing above the atmosphere. What changed is the meaning carried by that image. Once you know about drag, reboost, aging, debris, and controlled reentry, the station no longer represents escape from limits. It represents how intelligently people can live with limits for a very long time. That is why the final thesis belongs here and not at the beginning. The safest fall is the fall still under command. Notice what that means. It does not mean the station was always doomed in a theatrical sense. It means the station was always part of a system that required care, and therefore always part of a future that required an ending strategy. The project was never failing because it needed maintenance. Maintenance was the condition of success. A planned end is the same kind of condition, simply seen later in the life of the machine. There is a quiet beauty in that if we are willing to accept a less childish idea of beauty, not the beauty of immortality, the beauty of honesty. Human beings built a place in orbit. They kept it alive with repeated competence. They learned from it. They shared it. And when the right time comes, they intend to bring it down deliberately, rather than pretending that the sky will keep their responsibilities forever. That is not defeat, it is discipline. The orbit was never passive. The station was never simply hanging there. What looked from the ground like effortless endurance was actually a long chain of interventions. That chain is what made the station possible. It is also what gives the ending its meaning. A controlled descent is the final link, not an interruption. So if someone asks again why the station cannot stay in orbit forever, the answer is no longer one line long. The answer is the whole corrected picture. Low Earth orbit is still part of Earth. Drag never fully stops. Large structures age. Shared orbits ask for management. Future uncontrolled risk is still risk. Responsibility does not end when usefulness fades. A machine that needed care in life needs care at the end of life as well. The station still crosses the dark. The image is still beautiful. The difference is that now the beauty includes the hidden work beneath it. Once that work becomes visible, forever stops looking like the natural outcome. It starts looking like the myth. That myth was never harmless. It encouraged people to confuse distance with exemption and endurance with permanence. The station gives us something better than that myth. It gives us a visible example of what continuous care can accomplish in a place that never stops resisting us. It also gives us the chance to end that example without pretending the resistance ever vanished. Seen that way, the station's final descent becomes less like a contradiction and more like a final translation. During its life, the hidden work stayed mostly invisible. At the end, the hidden work becomes explicit. The same seriousness that kept the station alive now has to guide it back down. The mission reveals itself completely only in that last decision. That final translation matters because it rescues the station from two bad myths at once. One myth says the station is a monument that should remain visible no matter what. The other says the station's end will prove that the whole project was fragile from the start. Both myths miss the adult reality. The project was strong enough to survive for decades precisely because people kept meeting its limits without denying them. A planned descent does not cancel that strength. It reveals the same strength in a different form. So the station's final meaning may be stronger than the first image suggested. In its earliest image, the ISS seemed to represent escape from the ordinary friction of Earth. By the end of the question, it represents something more demanding and more admirable. It represents human beings learning to work inside limits without pretending those limits have disappeared. That is a better kind of achievement than simple permanence would have been, because it tells the truth about what spaceflight really asks of the people who keep it going. Seen that way, the station's final lesson may be simpler than any single technical detail. Human work in orbit is strongest when it refuses to confuse endurance with exemption. The ISS endured because people kept respecting the environment around it. Its ending belongs to the same pattern of respect. That continuity is what makes the whole story feel complete instead of broken. Above Earth, the International Space Station will still look calm for as long as it remains there. That is part of its power. Great machines often hide their effort when seen from the proper distance. A bridge does not show every inspection. A ship on the horizon does not show every repair. The station crossing over the blue edge does not show every correction, every calculation, every burn, every avoidance plan. every judgment about hardware that has lived in orbit for years. From the ground, it is easy to fall in love with the still image, a bright human-made outpost above the world, familiar, reassuring, almost permanent. But the station was never a thing placed outside time. It was never a monument hung beyond consequence. It has always been a machine in a difficult address. The atmosphere never ended as cleanly as our imagination wanted, so drag kept reaching it. The orbit never sustained itself, so people kept restoring it. The structure never stopped aging, so teams kept extending, maintaining, and judging what could still be trusted. The environment never stopped being shared, so tracking and avoidance remained part of the cost of being there. The object was never small, so the end of its life could never be treated casually. That is the whole story in its simplest form. The station cannot stay in orbit forever because orbit, at least here, is not a place where human responsibility can be stored and forgotten. It is a place where responsibility has to be exercised continuously and eventually completed. A controlled descent therefore says something larger than goodbye. It says that a civilization serious enough to build in orbit must also be serious enough to end in orbit well. Not with panic, not with denial, not with a sentimental refusal to plan, with command, with restraint, and with a clear understanding of who bears the risk if planning is avoided. That makes the final act of the station strangely consistent with everything that came before it. The ISS has always depended on deliberate care. Life support is deliberate care. Docking operations are deliberate care. Reboost is deliberate care. Inspection is deliberate care. Debris avoidance is deliberate care. A planned deorbit is that same care expressed one last time in a different direction. So the right way to remember the station is not as a ruined dream of permanence. It is as proof that human beings can do something harder than permanence. We can build in a place that resists us, keep a giant structure alive there through years of work, and then admit that the proper end of care is not always indefinite preservation. Sometimes the proper end of care is to bring the thing home as safely as possible while control is still ours. When the station finally leaves orbit, the sky above Earth will lose a familiar object, but the deeper lesson it leaves behind will remain. Every future structure we build in low Earth orbit will carry the same invisible sentence inside it from the beginning. This place is useful. This place is not permanent. And anything we build here will one day have to answer both truths at once. The station taught us how to live in orbit for long stretches of time. Its ending may teach us how to leave orbit responsibly when the time comes. That is not a smaller lesson. It may be the one that decides whether everything built after it deserves the same kind of trust. If that lesson is taken seriously, then the station's disappearance from the sky will not mean its meaning has faded. It will mean one of its most important meanings has finally become impossible to miss.